The ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Here, take a look at this vector field, and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field, evaluated at all of those points that act like sources, will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out two-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point, you also think about the fluid flow around it, but this time, you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom, but quick up top, resulting in a net clockwise influence. And really, true proper curl is a three-dimensional idea, one where you associate each point in 3D space with a new vector characterizing the rotation around that point according to a certain right-hand rule. And I have plenty of content from my time at Khan Academy describing this in more detail if you want, but for our main purpose, I'll just be referring to the two-dimensional variant of curl, which associates each point in 2D space with a single number rather than a new vector. As I said, even though these intuitions are given in the context of fluid flow, both of these ideas are significant for other sorts of vector fields. One very important example is how electricity and magnetism are described by 4 special equations. These are known as Maxwell's equations, and they're written in the language of divergence and curl. This top one, for example, is Gauss's law, stating that the divergence of an electric field at a given point is proportional to the charge density at that point. Unpacking the intuition for this, you might imagine positively charged regions as acting like sources of some imagined fluid, and negatively charged regions as being the sinks of that fluid. And throughout parts of space where there is no charge, the fluid would be flowing incompressibly, just like water. Of course, there's not some literal electric fluid, but it's a very useful and a very pretty way to read an equation like this. Similarly, another important equation is that the divergence of the magnetic field is 0 everywhere. And you can understand that by saying that if the field represents a fluid flow, that fluid would be incompressible, with no sources and no sinks. It acts just like water. This also has the interpretation that magnetic monopoles, something that acts just like a north or a south end of a magnet in isolation, don't exist. There's nothing analogous to positive and negative charges in an electric field. Likewise, the last two equations tell us that the way that one of these fields changes depends on the curl of the other field. And really, this is a purely three-dimensional idea, and a little outside of our main focus here. But the point is that divergence and curl arise in contexts that are unrelated to flow. And side note, the back and forth from these last two equations is what gives rise to light waves. And quite often, these ideas are useful in contexts which don't even seem spatial in nature at first.